Good morning to you all, dear students. Today's video I am making mainly on F block elements. These F block elements are also referred as inner transition elements. We need to understand what is the exact meaning of inner transition elements. Let's see here, if you consider any orbital present. So this is positively charged nucleus. I have one orbital present over here. Then I have second orbital is present. Then I have lastly third orbital is present. When you consider any atom with a nucleus, it is said to be exactly center part of the atom. Now I have the outermost shell, which is called as last valence shell of an atom. Fine. So next to that I will be having n minus 1 orbital. Say for example I will be having n minus 1 d orbital is present. Fine. So n minus 1 d orbital is said to be penultimate orbital. What we call it as? We call it as penultimate shell or penultimate orbital. Right. Then I have next to this one, inside if you move, n minus 2 orbital is present. And this n minus 2 orbital generally preferred F block, that is F block elements generally written here. So n minus 2, what is present inside the penultimate shell, that is referred as anti-penultimate shell. That is referred as anti-penultimate shell or anti-penultimate orbital. So these are generally a general information regarding these F block elements I am giving you. So n minus 1d is said to be penultimate shell and last one is said to be valence shell, and n minus 2 if you are preferring, then we will be calling it as inner shell to that of the penultimate shell. And the reason we will be calling them as anti-penultimate shells. So anti-penultimate shells will be found inside to the penultimate shells. Right? So as they are retaining very inside to that of the valence shells and penultimate shells, we will be calling them as inner transition elements. We have discussed regarding the transition elements. All the D block elements are referred to be transition elements, and after D only, that is inside, we will be finding the F block elements. The reason why they are called as inner transition elements. So if you particularly consider F block elements, there are mainly two series we have. So let's see one by one what are those things, how do they have been categorized and all. Okay, so F block elements have been categorized mainly into two series. Two series of elements are present. So F block elements have been categorized into two series. What are they? One is said to be 4F series and other is said to be 5F series. So these have been classified, that is 4F series and 5F series. When you consider 4F series, they all are said to be Lanthanides. They are all said to be Lanthanides. So Lanthanides belongs to 4F series. So this is the first point we have understood. Like that, we have next series which belongs to Actinides, to which Actinides are present in 5F series. 5F series. So in total we have two types of series, and each of these series are made of, or they are allotted with that of 14 elements. 14 elements are generally present. Now when you consider Lanthanides and Actinides, as name itself suggests, these are called as inner transition elements. Inner transition elements is mainly called because these are called as inner transition elements. These are called as inner transition elements. Why? Why is mainly because the last electron enters to n minus 2 f sub shell. That was the reason why these are called as inner transition elements. Like that, if you write the electronic configuration for F block elements, if you are writing here, I would tell you that electronic configuration becomes, we will be having noble gas configuration, then we will start with filling the F block, that is n minus 2. What was the capacity? As I told you, F 1 to 14 electrons will be present. Then comes penultimate shell, that is D. D has capacity from 0 to 10. Or some of the orbitals may become 0 also. Then I have NS2, that is NS1 to 2 electrons will be present. So if you ask for general electronic configuration for F block elements, okay, then you supposed to remember this one. This can be asked for your 1 marks. This is 1 mark question. So came to know all the idea what I told you. First and foremost, F block elements are called as inner transition elements. Inner transition elements name is given mainly because last electron enters to anti-penultimate shell. I have given you clear idea regarding the penultimate shells and anti-penultimate shells. Then moving to F block elements have been categorized into lanthanides and actinides. Lanthanides series is referred as 4F series. Actinide is referred as 5F series. Inner transition elements, I explained. Electronic configuration, if you want to write, noble gas N minus 2, because it is anti-penultimate shell, must be written first. 1 to 14 electrons can be filled here. Then we have N minus 1, N minus D, 0 to 10 electrons, then NS2. So these are all about the brief introduction for F block elements. Do copy, we'll move to next. Dear students, now let us begin with the lanthanoids. So lanthanoids, if you consider atomic number from 58 to 71, all the elements are said to be lanthanoids. And it starts from cerium and it ends to lutetium. So these all are said to be, with atomic number 58 to 71, all are said to be lanthanoids. This is the first point. Then if you particularly write the electronic configuration for lanthanide series, what I have written here, it is electronic configuration for particularly lanthanoid series. Fine. Now moving to the most important terminologies, they are lanthanoid contraction and imperfect shielding. Let me first explain you regarding lanthanoid contraction. What exactly the meaning of contraction? Contraction in the sense shrinking, squeezing. Squeezing or shrinking reduces size of any element. The lanthanide contraction is going to take place in these elements. Why? Fine. So we know that they will be starting from atomic number 58 and ends to atomic number 71. Why do they contract? What is the main reason for lanthanoid contraction? First, let me tell you, gradual decrease in atomic size. Gradual decrease in atomic size of lanthanide elements or of lanthanoids is referred as lanthanoid contraction. Getting? ಏನಾಗ್ತದೆ, first element ನೀವು consider ಮಾಡಿದ್ರ, it starts, okay, first elements to last element, what will happen? Size is going to be decreased. What exactly we have studied in the general trends? In general trends, when we move from left side to right side, there will be a gradual decrease of size, right? Now similarly, if you consider for lanthanides, Lanthanoid contraction we have seen. Here also we will be seeing a gradual decrease of the atomic size. The atomic size decrease, what is the difference ma'am? ಅಲ್ಲಿ ಜನರಲ್ ಟ್ರೆಂಡ್ಸ್ ಒಳಗೆ ಸೈಜ್ ಕಡಿಮೆ ಆಗುತ್ತೆ ಅಂತ ಹೇಳಿ ಓದಿದ್ವಿ, ಇಲ್ಲಿನೂ ಕೂಡ ಸೈಜ್ ಕಡಿಮೆ ಆಗುತ್ತೆ ಅಂತ ಓದಾಕತ್ತೀವಿ. ಇದಕ್ಕೆ ಯಾಕೆ ಸಪ್ರೇಟ್ ಆಗಿ ಲ್ಯಾಂಥನಾಯ್ಡ್ ಕಾಂಟ್ರಾಕ್ಷನ್ ಅಂತ ಹೆಸರು ಕೊಟ್ಟಾರ? ಇದು ಏನು ಸ್ಪೆಷಲ್ ಐತಿ? ಎಸ್, ದೇರ್ ಇಸ್ ಅ ಸ್ಪೆಷಾಲಿಟಿ. ಏನಾಗ್ತೈತಿ ನೋಡ್ರಿ, ಜನರಲ್ ಟ್ರೆಂಡ್ಸ್ ನಾವು ಪೀರಿಯಾಡಿಕ್ ಟೇಬಲ್ ಇಂದ ಕನ್ಸಿಡರ್ ಮಾಡಿದ್ರೆ ಎಫೆಕ್ಟಿವ್ ನ್ಯೂಕ್ಲಿಯರ್ ಚಾರ್ಜ್ ಏನಾಗ್ತಿತ್ತು, ಲೆಫ್ಟ್ ಸೈಡ್ ಟು ರೈಟ್ ಸೈಡ್ ಇನ್ಕ್ರೀಸ್ ಆಗ್ತಾ ಇತ್ತು. And there was a kind of particular difference between these elements. ನಾವು ಲೆಫ್ಟ್ ಸೈಡ್ ಇಂದ ರೈಟ್ ಸೈಡ್ ಹೋದಾಗ ಮೇಲ್ಗಡೆ ಇರುವಂತಹ ಎಲಿಮೆಂಟ್ಸ್ ಅದರೊಳಗೆ ಏನಾಗ್ತಿತ್ತೆ, ಪರ್ಟಿಕ್ಯುಲರ್ ಡಿಫ್ರೆನ್ಸ್ ವಿ ವುಡ್ ಬಿ ಪ್ರೆಡಿಕ್ಟಿಂಗ್. ಆ ಡಿಫ್ರೆನ್ಸ್ ಎಷ್ಟು ಇರ್ಬೇಕಿತ್ತಲ್ಲ ಅದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಡಿಫ್ರೆನ್ಸ್. ದಟ್ ಮೀನ್ಸ್ ಈ ಕಾಂಟ್ರಾಕ್ಷನ್ ಒಳಗ, ಲ್ಯಾಂಥನಾಯ್ಡ್ ಕಾಂಟ್ರಾಕ್ಷನ್ ಒಳಗ ಎಷ್ಟು ಎಕ್ಸ್ಪೆಕ್ಟೆಡ್ contraction ಇರಬೇಕಿತ್ತಲ್ಲ ಅದಕ್ಕಿಂತ ಜಾಸ್ತಿ contraction we can see here. Very smaller the size of the elements than expected is seen. That is the main reason. Gradually decrease in the atomic size we can be seen here. Now question arises, next point, that is shielding. I must have to explain this point to you in detail. What exactly meaning of shielding we already discussed in the chapter P block elements, right? So same criteria is going to apply here. I'll make some space by rubbing this one. Hope you have taken. So here I'll explain the things in detail to you once again. So now we supposed to study this lanthanoid contraction in detail also. Let's see shielding effect. Okay, so imagine this is the nucleus. Nucleus ಸುತ್ತಲೂ ಏನೈತಿ, first orbital is present. Then I have second orbital is present. Then I have third orbital is also present. Agree? ನೋಡ್ರಿ, ನ್ಯೂಕ್ಲಿಯಸ್ ಹತ್ರ ಇರುವಂತದ್ದು ಯಾವ್ದಪ್ಪ, ಇದು ಫಸ್ಟ್ ಶೆಲ್ ಇರುವಂತದ್ದು ಯಾವ್ದಿದೆ, ದಿಸ್ ಈಸ್ ಎಸ್. And S shell has got certain electrons which are completely in the influence of nucleus. I'm sorry, only 2 electrons will be present. So what will have, this nucleus will have highest hold on these electrons than that of the valence shell electrons. ಹೌದಾ? ಅಂದ್ರೆ ನ್ಯೂಕ್ಲಿಯಸ್ ಈ ಎರಡು ಎಲೆಕ್ಟ್ರಾನ್ ಅನ್ನ ಅಥವಾ ಎಸ್ ಎಲೆಕ್ಟ್ರಾನ್ ಅನ್ನ ಕ್ಲೋಸ್ಲಿ ಅಸೋಸಿಯೇಟೆಡ್, ಅಂದ್ರೆ ಟೈಟ್ ಆಗಿ ಹಿಡ್ಕೊಂಡಿರ್ತದೆ, ಒಟ್ಟು ಬಿಡಂಗಿಲ್ಲ. This is condition with respect to s electrons. Soon after that we will be having certain electrons in P, certain electrons present in D, and so on. There will be certain electrons are present, right? Imagine electrons are present. Now if you consider, right, if you consider this is anti-penultimate shell and this is penultimate shell. This is 2s, this is 1s, inside it is present. So this is said to be anti-penultimate shell, n minus 1 f, right? This is imagine it is D shell. Correct agi artha madkori. Here what will happen here, generally what do the P block elements do? If you consider P block elements, generally P block elements show certain kind of exhibition, or S block elements will also show certain kind of exhibition that nucleus cannot, in nucleus ಏನೈತಲ್ಲ, it will be having hold of on all the electrons, right? Inner shells, these inner shells are so strong that they will put a wall. ಏನ್ ಮಾಡ್ತಾವು, ಫಸ್ಟಿಗೆ ಈ ತರ ಸ್ಟಾಪ್ ಮಾಡಿ ನಿಂತು ಬಿಡ್ತಾವ. ನ್ಯೂಕ್ಲಿಯಸ್ ಏನ್ ಮಾಡ್ಬೇಕು, ಫಸ್ಟ್ ತಮ್ಮ ಎಲೆಕ್ಟ್ರಾನ್ ಅನ್ನ ತಗೋಬೇಕು, ತಮ್ಮನ್ನ ಪೂರ್ತಿ ಕಂಟ್ರೋಲ್ನಾಗ ಇಟ್ಕೋಬೇಕು. ಅನ್ಲೆಸ್ ದೇ go under the control of the nucleus, they will not allow other electrons to go into that one. That is called as shielding effect. ನ್ಯೂಕ್ಲಿಯಸ್ ಹೊರಗಡೆ ಇರುವಂತ ಎಲೆಕ್ಟ್ರಾನ್ ಅನ್ನ ತನ್ನ ಕಂಟ್ರೋಲ್ ಒಳಗೆ ಇಟ್ಕೊಳ್ಳದೆ ಇರೋ ತರ ಇವೇನ್ ಮಾಡ್ತಾವ, ಶೀಲ್ಡ್ ಮಾಡ್ತಾವ. ಇಲ್ಲಿ ಒಂದು ಶೀಲ್ಡಿಂಗ್, ನೀವು ಕೆಮಿಸ್ಟ್ರಿ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡುವಾಗ ಬ್ಲ್ಯಾಕ್ ಕಲರ್ ಇಂದ ಹಿಂಗೆ ಇಟ್ಟಿರ್ತಾರ. ಎದಕ್ಕೆ ಇಟ್ಟಿರ್ತಾರ, ಜೋರಾಗಿ ಗಾಳಿ ಬಂದು ಬನ್ಸನ್ ಬರ್ನರ್ ಆಫ್ ಆಗಬಾರ್ದಂತ ಶೀಲ್ಡಿಂಗ್ ಇಟ್ಟಿರ್ತಾರ. ಶೀಲ್ಡ್ಸ್, ಬ್ಲ್ಯಾಕ್ ಕಲರ್ ಶೀಲ್ಡ್ಸ್ ಇಟ್ಟಿರ್ತಾರ, ಗಾಳಿ ಬಂದು ಯಾವುದೇ ರೀತಿ ಬರ್ನರ್ ಆಫ್ ಆಗಬಾರ್ದು ಅಂತ ಹೇಳಿ. ಅದೇ ಥರ ಇವು ಏನು ಮಾಡ್ತಾವು, ಇನ್ನರ್ ಶೆಲ್ಸ್, they will shield or they will put a kind of strong forces or strong shield here, so that nucleus cannot have hold on outer electrons. Okay, ಆ ತರ ಕಂಪ್ಲೀಟ್ ಆಗಿ ಶೀಲ್ಡ್ ಮಾಡಿದಾಗ they are referred as good shielders. Good shielders. They are called as good shielders, and shielding effect will be more. Shielding effect is more. Okay, so higher the shielding effect prohibited by inner shells, larger will be the size. I repeat, higher the shielding effect exhibited by inner shells, larger will be the size. ಯಾಕಂದ್ರೆ ನ್ಯೂಕ್ಲಿಯಸ್ ಔಟರ್ ಎಲೆಕ್ಟ್ರಾನ್ ನ ತನ್ನ ಹೋಲ್ಡ್ ಒಳಗೆ ಇಟ್ಕೊಳ್ಳಂಗಿಲ್ಲ. ಇವು ಎಲ್ಲಿ ಬೇಕಲ್ಲ ಬೇಕಾಬಿಟ್ಟು ಅಡ್ಡಾಡಕ್ ಹತ್ಬಿಡ್ತಾವ. ಸೊ ಒಂದೊಂದ್ಸತ ಇಲ್ಲೇ ರಿವಾಲ್ವ್ ಹೋಗ್ತಾವ, ಒಂದೊಂದ್ಸತ ಇಷ್ಟು ದೂರ ಹೋಗಿ ಬರ್ತಾವ, ಮತ್ತೆ ಇಲ್ಲಿ ರಿವಾಲ್ವ್ ಹೋಗ್ತಾವ. ಸೊ ಬಹಳಷ್ಟು ಸ್ಪೇಸ್ ಉಳಿದ್ಬಿಡ್ತೈತೆ ಅವಕ್ಕೆ. Because nucleus cannot control them, cannot have hold on them, so they will start moving here and there and all happens. ಆ ತರ ಮೂವ್ ಆಗೋದ್ರಿಂದ ಏನಾಗ್ತೈತಿ, size is going to be increased. Very good shielders, if you consider, they are generally S shells, that is S subshells and P subshells. S subshell ಇಂದ P subshell ಇಂದ shielding effect comparatively ಜಾಸ್ತಿ ಇರ್ತೈತಿ than that of F and D. These, at least if you consider F block elements, they are poorest shielders. They do not exhibit any kind of shielding effect as that of the other S and P does. Even if you consider D orbitals, they will also don't show a kind of shielding than that of the stronger S and P. So these are F block elements. What we consider here are poorest shielders. ಅವು ಏನು ಮಾಡ್ತಾವು, ಈ ರೀತಿ ಹಿಂಗ they must have put some effect here. The shielding effect must be done here. But ಅವು ಏನು ಮಾಡ್ತಾವು, ನ್ಯೂಕ್ಲಿಯಸ್ ಹೋಗಿ ನ್ಯೂಕ್ಲಿಯಸ್ ಎಲ್ಲ ಎಲೆಕ್ಟ್ರಾನ್ ಅನ್ನ ನೀನು ಕಂಟ್ರೋಲ್ ಆಗಿ ಇಟ್ಕೋ, ನಾನು ನಿಂಗೇನು ಪ್ರಾಬ್ಲಮ್ ಮಾಡಂಗಿಲ್ಲ. This F block says. So what happens, due to poor shielding effect, imperfect, or due to poor shielding of F block elements, Z effective nuclear charge increases. Remember, once the effective nuclear charge increase ಆಯ್ತಿಲ್ಲೋ, ಏನ್ ಮಾಡ್ತೈತಿ ನ್ಯೂಕ್ಲಿಯಸ್, ಎಲ್ಲ ಎಲೆಕ್ಟ್ರಾನ್ ಅನ್ನು ಬರ್ರಿ it will start taking all the electrons inside like this. If they start taking electrons inside like this, what will happen? Size decreases. Expected size ಎಷ್ಟಿತ್ತಲ್ಲ ಅದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಸೈಜ್ ಏನಾಗ್ತದೆ, ಕಡಿಮೆ ಆಗ್ಬಿಡ್ತೈತಿ. That is called as lanthanide contraction. That is called as lanthanide contraction. Gradual decrease in the atomic size of the elements leads to shrinkage of the size than expected. That is called as lanthanide contraction. Lanthanide contraction is mainly because what? Imperfect shading or poor shading of inner shells. Inner shells do not shield outer electrons in such a manner that effective nuclear charge increases. Nucleus starts grabbing all the electrons towards itself. That is the reason why shrinkage of size is seen. That is called as lanthanide contraction. I hope this is clear for you all. If it is so, we will have certain consequences. So consequences of lanthanide contraction will understand, and consequences of lanthanide contraction can be asked for 3 marks. Do copy this. We'll move to next. Dear students, now I have written some of the consequences of lanthanide contraction. Let us understand what are these consequences. So due to gradual change, what exactly expected doesn't happen. There's something other thing which is unexpected that's happened. Due to that unexpected things happen with respect to lanthanide elements, we have got some of the changes with the respective properties also. They are called as consequences of lanthanide contraction. From atomic radii, that is from zirconium to hafnium, it almost remains the same. So zirconium being a d block element, the size is going to be remaining same, that is almost the same, it remains. Lanthanoids would have shown a different atomic radii from that of the d block elements. So we know that from down the group what has happened, down the group general trends, if you consider, size would have been increased. I'll show you with the help of periodic table. Give me some time here. So very first point, let's understand here with the help of periodic table. See, I have zirconium from d block element. From zirconium to hafnium they are telling. So we have lanthanides here. Okay, zirconium being a d block element, from here to here, zirconium and hafnium being they are d block elements, their size is remaining same here, yet we have introduced 14 elements. These 14 elements, due to lanthanide contraction, they will have got size is go on decreasing. Size is went on decreasing. As these D elements also come across with these F block elements, actual size from zirconium to hafnium, it would have increased, because we know general trend down the group size of elements increases due to adding of penultimate shells or number of shells. Number of shells are increasing, size would have been increased, but we have interfering, these are interfering elements, they are lanthanides, which are come across the D block elements. Due to reason why zirconium to hafnium, there is no gradual increase in the size, rather the size of these elements go on remaining same. I have written here a value, you can see. From atomic radii from zirconium to hafnium, it is almost the same. It is 168 and it is 159. There would have been a large increase in the size, but it is remaining same due to lanthanide contraction. That was one of the consequences of they are affecting other elements also. Coming to the next one. As the size is remaining here same, we cannot easily separate them. It will become separate. The zirconium elements, that is D block, from zirconium to hafnium, there is size remaining same. We couldn't identify, we couldn't separate them with respect to their properties. That was also one of the consequences. Next what we have, covalent character of cations is increasing. See, it is very important point. See here, covalent character is increasing. General trends what we have seen from left to right, effective nuclear charge was increasing. As effective nuclear charge was increasing, it was highly difficult to take the electrons very easily. But what will happen here, due to this lanthanide contraction, instead of effective nuclear charge increase, what had happened here, can you see? We have seen covalent character. Covalent character means what? These all are seems to be non-metals. We have metals, metallides, non-metals in P block elements. Agree. But non-metallic character, what is happening here? It is going to be, it would have been decreased. But according to if you consider lanthanoid contraction, covalent character of cations is increasing. Covalent character is increasing of cations. That is also one of the character. Covalent character increases in the sense almost they remain non-metals, further we move. That was the second point. Next, if you see here, that is electronegativity of trivalent ions is increasing slightly. Electronegativity value is nothing but what? Tendency to accept or grab a paired electrons. Bond paired electrons are taken away from the atom, that is called as electronegativity. Electronegativity generally would have increased it But after removing some of the electrons from the cation, then they will become trivalent ions. Then it is going to be increased. Electronegativity of trivalent ions, they are increasing. Direct element in the electronegativity increase agಬೇಕಾಗಿತ್ತು. But after making changes with respect to electrons, that is removal, when trivalent ions are becoming, then electronegativity is increasing due to lanthanide contraction. That is also one of the consequences. Coming to the next one, basicity decreases from lanthanum to lutetium. So can you see here, basicity point they are speaking here. We have lanthanum here and we have lutetium. Basicity value actually would have been increased. Why it would have been increased? Because we know that metallic character is going to be decreased. We would have taken electron very easily. What is basic nature? Basic nature is nothing but we will be taking H plus easily from any element. Basicity actually increase agbekiತ್ತು. Basicity increase aglarde basicity starts decreasing. That was also considered as one of the consequence of lanthanide contraction. Coming to the next, standard potential electrode values. This is most important. What is a standard potential? That is, if you have any elements present in their original state, they will be having their stable configuration. Stable configuration ಒಳಗೆ ಇರುವಂತ molecules doesn't want to change with respect to their ionic form. Okay, I repeat my word. Stable form ಒಳಗೆ ಇರುವಂತ ions, they doesn't undergo any ionic form. In the sense, they neither want to accept nor want to donate the electrons. They will be remain happy as they are already there. But standard electrode potential value is going to increase here. Due to lanthanide contraction, standard electrode potential value, that means from stable configuration to ionic configuration change aglike, they will tend to become ionic to obtain their stability. That point is going to be increased. That is called as standard electrode potential value is went on increasing. This is standard electrode potential, that is SRP, reduction potential, oxidation potential. You will be learning in detail in the chapter electrochemistry. Till then, just remember, these are the considered as consequences for lanthanide contraction. So these are the important points. Any of the 2 to 3 points can be asked for your exam. That is, write any consequences of lanthanide contraction. So please do copy this. We'll move to next. Coming to the next point regarding properties of F block elements. When you consider their properties in physically, if you see these metals, they are silvery white color in nature. Silvery white metals, they tarnish rapidly in the air. They give a kind of sparkle type of light when they exposed to air. Second point, hardness is going to be increased with increase in atomic number. As atomic number increases from lanthanums to actinides, lanthanides to actinides, due to increase in the atomic number of electrons increases. We know that interstitial compounds plays important role. Again, hardness also increases. Next point, if you consider, they show they are also good conductors of heat and electricity. Due to unpaired electrons presence, they show kind of heat and electricity. Next point, they show a coloring property. We explained coloring property is due to transition of the electrons. They will be moving to the higher energy state due to absorption of certain amount of energy. When they reach higher energy state, they are unstable. In order to get their stability back, they will be coming back from excited state to the ground state. While coming back, they will be liberating certain amount of energy that is visible in the visible range in the form of color. Coloring property of F block elements is also seen to the larger extent. Some of the exceptions are also there due to some of the Leaving some exceptions, we also see the coloring property in F block elements also. Coming to the next one, due to presence of unpaired electrons, I repeat, presence of unpaired electrons. If it is completely filled, then it is said to be diamagnetic. If you have any unpaired electrons present in their ground state as well as in their excited state or either of them, then they are considered as paramagnetic. They affect the magnetic field. They attract the magnetic field. There are certain exceptions are also present in the F block elements. Leaving them all shows a kind of magnetic property also. So these are said to be important characteristics of F block elements. Do copy this. We'll move to next. Dear students, in this video we will understand regarding some of the chemical properties of lanthanides. We have discussed lanthanides, what are the elements which are present in lanthanides, what is the general configuration, what is the electronic configuration for lanthanide series, all those things we discussed. Consequences of lanthanides also we have completed. In this video, we will understand some of the chemical properties of lanthanides. When lanthanides undergo treatment with excess of oxygen atom, they will form lanthanide oxides. And lanthanides combine with hydrogen atom. When they are gently heated, they will form hydrides. Lanthanide hydrides are formed. Similarly, lanthanides form corresponding carbides also, as we have seen these reactions, carbides formation in the chapter hydrocarbons first year. Similarly, lanthanides will form corresponding carbides when they are heated with carbon. The temperature is to be very high, that is 2773 Kelvin. So these are the important characteristic chemical properties. We also have some of the other properties. Let's see them. So here we have some of the other important reactions of lanthanides. When lanthanides are generally treated with carbon, as I told you, carbides they are going to form. Similarly, they liberate hydrogen atom from the dilute acids. They will give reaction with dilute acids also. Hydrogen gas is going to be liberated. When lanthanides burn in halogens, they will form halides also. Lanthanide halides also formed. Reaction with water, they will form hydroxides. See here, hydroxide also formed. From nitrides, if you consider, they are heated with nitrogen, they will form the nitrides. Lanthanides react with sulfur also and they will form corresponding sulfides. Nitrides, sulfides as well as carbides and hydroxides, and reaction with dilute acids also they will show certain extent of reaction. So these all reaction, around 8 reactions are seems to be chemical properties for lanthanides. Do remember these questions, in the sense practice these reactions. That is, lanthanides will form hydroxides, they will react with dilute acids, they will give us sulfides. Nitrogen reaction also gives nitrides and so on. You have to remember. Out of these can be asked one question for 1 marks. Coming to the next part, that is the actinides. Actinides starts from the atomic number 90 and to the 103. There are 14 elements are present in actinides from thorium to lawrencium. All these series elements are called as actinides, and these elements are going to be referred as 5f orbitals. They will be entered into 5f orbital. So these are considered to be actinides. General electronic configuration, if you refer here for actinides, it is Rn 5f1 to 14. See the d orbital 6d 021 7s2 is the general electronic configuration for actinides. So there is a actinide contraction also we can see here as that of the lanthanide contraction. Gradual decrease in the size of the atoms actinides across the actinide series itself is called as actinide contraction, as that of the lanthanide contraction, which I explained you with the help of a penultimate shell and antipenultimate shell. Similarly, we can see actinide contraction also. Actinides show greater number of oxidation states. Again, there is a variation in participating electrons. 5f 6d 7s, all the electrons are participating. The reason why they will be showing variable oxidation states. If you consider common oxidation state or the minimum oxidation state for actinides as well as for lanthanides, it is +3. Generally, very commonly, they will be present in +3 oxidation state. The variable oxidation states for the actinides, if you consider, they may lose 3 electron, 4, 5 and up to 7 electrons they will be losing. They will be losing up to 7 electrons. So they will have maximum oxidation state +7. When you consider the member of the lanthanide series which is well known to exhibit +4 oxidation state, it is cerium. Write the electronic configuration for cerium. Just go for the removal of the valence electrons. You will get the stability for electronic configuration for cerium. Write the electronic configuration and do it and try it yourself. If you don't get, I'll do it. Don't worry. So what is the highest oxidation state shown by the actinides? They have asked here, or they can also ask name an element that shows highest oxidation state, oxidation number among the actinides. It is N +7. Two elements will be showing +7 oxidation state, that is NP and PU. They are the symbols. Now coming to the general characteristics of actinides. So not so expected questions, so no any so much of important questions can be asked in this one, but we'll have the knowledge regarding actinides, their characteristics. Actinides are said to be radioactive silvery metals as that of the lanthanides. Highly reactive, finely divided state. They are in the sense when they divide it into very smoothly, that is very small particles, if they are going to be divided, then they will be giving us large surface area. Then actinides are slightly affected by concentrated nitric acid owing to the formation of protective oxide layers, but highly affected by hydrochloric acid. Acidic character, acidity, if you maintain here, they will be definitely affected. As there is a presence of unpaired electrons, we can consider these are paramagnetic in nature. Then coming to last point, they form oxocations in higher oxidation states like NPO plus UO2 plus. That is removal of 1 electron, 2 electron forms cations going to be stable in at higher oxidation state. These are the characteristics of actinides. Let's see what are the main differences for actinides and lanthanides. So when you consider a particularly differences, distinguish between lanthanides and actinides. In lanthanides, 4f series will be filled. In actinides, 5f orbitals will be filled. Here, these are exceptionally not radioactive. They are non-radioactive. Only PM, promethium, is radioactive. But in case of actinides, almost all are said to be radioactive in nature. Binding energies of 4f electrons is higher. Binding energy of 5f electrons are higher in actinides. Lanthanides are less basic. Actinides are more basic in nature. Maximum oxidation state, what we see here in lanthanides, it is +4, but in case of actinides, the maximum up to +7 oxidation state we can see. The 4f electrons have higher, greater shielding effect. I explained you what is the shielding effect. What is the effect, shielding effect, what it causes? It going to cause consequences for lanthanide contraction. Similarly, 5f electrons have poor shielding effect. Here 4f electrons have greater shielding effect, but in case of actinides, poor shielding effect is generally seen. That is almost nil, we can say, the shielding effect played in actinides. So the reason why more the lanthanides, size of these actinides will be very less. Lanthanoid contraction is lesser. Actinide contraction is greater. As I told you, actinides will be contracted so positively from the effective nuclear charge is mainly because almost shielding effect will be nil. So these will have smaller size than that of the lanthanides. Now Dear students, moving to the next part, that is applications of D and F block elements. They generally used in iron and steel. Construction materials we have seen in there, generally these F block elements are used. Some oxides of D elements like titanium oxide used as a pigment in industry. Manganese oxide generally used in dye battery cells like zinc and nickel cadmium, that is also used in battery cells. Fine. Then copper and nickel alloy formation I explained. In alloy formation also generally these D and F block elements are used. Titanium tetrachloride with this I explained. Ziegler-Natta catalyst I explained you. It is mainly used for manufacture of polythenes, that is gasoline. Gasoline is synthesized from the petroleum. There we used Ziegler-Natta catalyst. I explained this. This AgBr, silver bromide, has a special light sensitive property. It is used in photography. Special layer of this AgBr is applied on that one, so that the photographic effects will be very prominent. Then D elements are used as a catalyst in many industrial productions, and these also act as a catalyst in many industries. We have seen Haber's process, contact process, where we make use of some of these elements as a catalyst. Palladium chloride used as a catalyst in the oxidation of ethylene, that is Waker's process we have seen. Nickel complexes are useful for polymerization of alkynes. Organic compounds like benzene are synthesized. So these all are considered to be some of the applications of D and F block elements. Study of actinide elements is difficult. Give reason. Actinides all are radioactive. Half-life of actinides are very short. They couldn't be prepared in nanograms. Nanograms is we at least need nanograms for a spectroscopic studies. In that minute quantity also we cannot synthesize these, because they have very less short life, that is half-life is very short. Then coming to the last, composition of mixed metal. Please do remember this one. Mixed metal has been asked for your 1 marks question. This is 1 mark question. A typical composition of mixed metal, it is 50% cerium, 25% lanthanum with small amount of neodymium and praseodymium. This composition they have asked. This is 1 mark question, can be asked for your board examination. So with this last part of the applications part, we have successfully completed the chapter D and F block elements. Students, I do request you, please do complete the notes within a given time and practice. As much as you practice, the things will be memorized easily. So with this last part, I would like to tell the chapter is completed.